What if Earth is not special? What if the only reason we are alive is because our planet didn't make the same mistake Mars did? Right now, Mars is a frozen desert, a silent world covered in dust and scars from a violent past. Its sky is thin, its surface is bathed in deadly radiation. Liquid water cannot survive there. And yet, this wasn't always the case, because scattered across Mars are signs that should not exist on a dead planet. Dry river valleys carved into stone, lake beds that once held standing water, minerals that can only form in the presence of liquid water. Mars was once wet. Mars was once warm. Mars once had an atmosphere thick enough to support flowing rivers and changing seasons. In other words, Mars was once dangerously close to becoming a second Earth. So what went wrong? Why did two neighboring planets formed from the same cosmic material end up with such radically different fates? Why did one world become alive, while the other became a warning? Was Mars simply unlucky, or did it make a mistake written into its very structure from the moment it was born? And here's the most unsettling question of all. If Mars could lose its atmosphere, if Mars could lose its water, if Mars could lose its chance at life, then what guarantees that Earth won't follow the same path? The answers are not found in science fiction. They are written in ancient rock, buried beneath Martian dust, waiting to be understood. To uncover the death of Mars, we must go back to the violent birth of the solar system, back to a time when Mars and Earth were not so different, back to the moment when two planets took nearly identical paths, until one of them slowly, silently began to fall behind. 4.5 billion years ago, the solar system was not the calm, orderly place we see today. It was violent, chaotic, a swirling disk of fire, dust, and debris orbiting a young, unstable sun. From this cosmic storm, worlds were being born. Among them were two small rocky planets, forming close together, so close that, at first, there was almost no reason to believe they would end up so different. One would become Earth, the other Mars. Both planets were built from the same ingredients, the same cosmic dust, the same rock and metal, the same water-rich asteroids crashing into their surfaces during the solar system's early chaos. In their infancy, Mars and Earth were siblings formed in the same neighborhood, under nearly the same conditions. They were not strangers, they were twins in origin. Early Mars was not the cold, red desert we know today. It was warm, it was geologically active, and most importantly, it had energy. Deep inside both planets, radioactive elements were decaying, generating heat. This heat powered volcanoes, reshaped landscapes, and kept their interiors molten and alive. On early Mars, massive volcanoes erupted for millions of years, releasing gases into the atmosphere: carbon dioxide, water vapor, nitrogen, exactly the same gases that helped Earth form its life-supporting blanket of air. At this stage, Mars did not look like a failed planet. It looked promising. But even at birth, there was one quiet difference, so subtle it seemed unimportant at the time. Mars was smaller, not dramatically smaller, just enough to be overlooked. Mars formed faster than Earth, gathering material quickly but running out of nearby building blocks. Earth, slightly closer to the Sun and in a denser region of the disk, continued growing, becoming heavier, stronger, and better at holding on to its internal heat. Mars, meanwhile, stopped growing too soon. In the early days, this didn't matter. Both had thick atmospheres forming above their surfaces. Both were bombarded by icy asteroids, delivering water, vast amounts of it. For millions of years, Mars may have looked more Earth-like than Earth itself. Imagine standing on ancient Mars. The sky is thicker, the temperature is warmer. Volcanoes loom on the horizon, pumping gases into the air. Meteor impacts occasionally light up the sky, but between the chaos, a stable planet is emerging. Mars was not dead on arrival, it was alive with possibility. Gravity, though weaker than Earth's, was still strong enough to hold an atmosphere. Sunlight warmed the surface just enough, and beneath the ground, heat kept the planet active. For a long time, Mars followed the same script as Earth, but planetary history is unforgiving. Small differences compound. Because Mars was smaller, it began cooling faster. Its internal heat, so critical for long-term stability, started leaking away more quickly than Earth's. At first, nothing seemed wrong. Volcanoes still erupted. The atmosphere still existed. The planet still looked capable of sustaining something remarkable. But deep inside Mars, A clock had already started ticking. As its core slowly cooled, Mars was losing more than just heat. It was losing its ability to protect itself. Earth's larger size allowed it to keep its core molten for billions of years, generating a powerful magnetic field. Mars' smaller core, however, was already beginning to struggle. This was not an immediate catastrophe, no sudden explosion, no dramatic collapse. Just a slow, invisible shift, one that would take millions of years to reveal its consequences. At this stage in the story, Mars still had something crucial, something that would define whether it could truly become a living world. Because all the energy, all the atmosphere, and all the geology in the universe mean nothing without one simple ingredient, the ingredient that turns chemistry into biology. And Mars had it, not just a little, but possibly oceans worth. The same asteroid impacts that delivered water to Earth had done the same to Mars. And now, with a warmer climate and a thicker atmosphere, that water had somewhere to stay. It pooled, it flowed, it reshaped the planet. Mars was ready for its most Earth-like chapter. And to understand what truly went wrong, we must follow the water, because wherever water goes, the fate of a planet follows with it. As Mars cooled from its violent birth, something extraordinary began to happen on its surface. The gases released by volcanoes thickened the atmosphere, trapping heat from the sun. Temperatures stabilized, pressure increased, and water delivered by ancient asteroids and released from the planet's interior no longer vanished into space. It stayed. Not gentle showers like on Earth today, but heavy, persistent rainfall that reshaped the land. Water flowed downhill, carving channels through rock. It collected in lowlands, forming lakes that lasted thousands, perhaps millions of years. Across the planet, rivers formed. We know this not from imagination, but from the scars still visible today. Vast valley networks stretch across Mars, branching and curving exactly like river systems on Earth. They are not the result of sudden floods or single catastrophic events. They show erosion over long periods of time, slow, patient, persistent flowing water. In some regions, those rivers widened into deltas, fan-shaped deposits of sediment that only form when water flows steadily into a standing body, like a lake or ocean. These deltas are among the strongest pieces of evidence we have, because deltas mean stability. They mean water that didn't just appear once and disappear. They mean seasons, climate, time. In the northern hemisphere of Mars lies a vast, low-lying plain. But billions of years ago, this region may have held an ocean covering nearly a third of the planet. Imagine it. A Martian sky thicker and darker than today's pale pink haze, clouds drifting overhead, rivers emptying into a massive northern sea, waves lapping against rocky shores. This was not a brief experiment. Mars did not simply flirt with habitability. For a significant portion of its early history, Mars was stable enough for water to exist on its surface, something that requires a very narrow balance of temperature and pressure. And where there is liquid water, something else happens. Chemistry becomes complicated. Water dissolves minerals, transports elements, and creates environments where molecules can interact, combine, and evolve. On Earth, this is where life began, not in dramatic lightning strikes, but in quiet pools, shallow lakes, and slow-moving rivers. Mars had the same environments. Clay minerals found on Mars tell us that water interacted with rock gently over long periods. These are not the minerals of violence or catastrophe. They are the minerals of calm conditions. Conditions where microbes could survive. Conditions where life could begin. For a time, Mars may have been not just habitable but inhabited. But water is both a gift and a vulnerability. Because once a planet has surface water, it becomes deeply dependent on something else, its atmosphere. Water needs pressure to remain liquid. It needs warmth to keep flowing. And both of those depend on a stable atmospheric shield. Mars, smaller and weaker than Earth, was already beginning to feel strain. As time passed, the planet's interior continued to cool. Volcanic activity slowed. Less gas was released into the atmosphere to replace what was being lost. And above Mars, an invisible battle was underway. The sun source of all life was slowly becoming a threat. Without realizing it, Mars was approaching a tipping point. A moment where the balance that allowed rivers and lakes to exist would begin to collapse. At first, the changes were subtle. Rain became less frequent. Rivers flowed more slowly. Lakes began to shrink. As temperatures dropped, water started freezing at the poles and beneath the surface. Some of it evaporated into the atmosphere only to be carried away, molecule by molecule, into space. Mars was drying out. Not suddenly, not dramatically, but relentlessly. And still, the planet might have recovered if it had been able to protect what remained. But Mars had already lost something critical, something Earth still had and still has today. A planetary shield, a force powerful enough to stand between a world and the full fury of the sun. As Mars' rivers faded and its lakes retreated, the real cause of its downfall was not water itself but the silent loss of protection around the planet. Because without that shield, every breath of atmosphere Mars had left was exposed. And the moment Mars lost its defense, the fate of its water and its chance at life was sealed. To understand how an entire planet can be stripped bare, we must look not at the surface, but deep inside Mars to the moment its invisible armor disappeared. That invisible armor, the one Mars was slowly losing, was its atmosphere. Today, Mars' atmosphere is so thin that standing water cannot survive on its surface. Air pressure is less than 1% of Earth's. If a human stood there without protection, the water in their body would begin to boil not from heat, but from the lack of pressure. But this fragile shell is only a shadow of what once existed. Early Mars had a thick atmosphere, rich in carbon dioxide, water vapor, and other gases released by intense volcanic activity. This atmosphere did more than just surround the planet, it transformed it. Carbon dioxide trapped heat from the sun, creating a greenhouse effect that warmed the surface. Water vapor amplified that warming. Together, they stabilized temperatures, allowing liquid water to persist. This atmospheric blanket turned Mars from a frozen rock into a climate-controlled world. Seasons may have existed, weather patterns formed. Clouds gathered, moved, and released precipitation. The planet breathed in its own way, and just as on Earth, the atmosphere served another, even more critical role. It was a shield. High-energy radiation constantly pours out from the sun's solar wind, charged particles, and cosmic rays capable of tearing molecules apart. On Earth, we rarely think about this threat because we are protected. Mars once was too, but atmospheric protection is not just about thickness. It's about retention. A planet must be able to hold on to its gases over billions of years, and this is where Mars' early advantage began to erode, because gravity matters. Mars' weaker gravity made it easier for gas molecules, especially lighter ones like hydrogen, to escape into space. At first, this loss was slow, almost unnoticeable. Volcanoes replaced what was lost. The atmosphere remained thick enough to do its job. But as Mars cooled internally, volcanic activity declined. Less gas was released. The atmosphere stopped being replenished at the same rate it was escaping. The balance shifted. Still, even this alone might not have doomed Mars. Earth also loses atmosphere every day. The difference is not that Earth doesn't leak, it's that Earth is defended. The true guardian of a planet's atmosphere is not the air itself, but something far more powerful and invisible. A magnetic field. Generated by the motion of molten metal deep within a planet's core, a magnetic field deflects solar wind, guiding charged particles harmlessly around the planet, instead of letting them slam directly into the atmosphere. Earth's magnetic field is strong, dynamic, and alive. It wraps the planet in a protective bubble, the magnetosphere. Mars once had one too. Evidence preserved in ancient Martian rocks shows that early Mars generated a global magnetic field billions of years ago. For a time, Mars stood protected, its atmosphere shielded from the sun's full force. But Mars was smaller. Its core cooled faster. As heat escaped into space, the molten motion inside the core slowed. Eventually, it weakened beyond recovery. The Martian magnetic field began to fade. Not overnight. Not in a dramatic collapse, but steadily until one day it was gone. Without a magnetosphere, Mars was exposed. The solar wind now struck the atmosphere directly, particle by particle, stripping it away into space. Carbon dioxide molecules were torn apart. Water vapor was broken down, its hydrogen escaping forever. E.N.B. eroded from above. As the atmosphere thinned, the greenhouse effect weakened. Surface temperatures dropped. Water began to freeze or sublimate into vapor, which only made things worse. A thinner atmosphere meant less protection, less heat. Mars had entered a feedback loop, a slow-motion collapse from which it could not escape. This was the moment Mars crossed a critical threshold, not the loss of water, not the loss of warmth, but the loss of defense. From this point forward, Mars was no longer fighting for habitability. It was fighting to retain what little it had left, and the Sun, relentless, indifferent, and powerful, continued to do what it has always done. It stripped away anything unprotected. The planet that once had rivers, lakes, and possibly oceans was now bleeding its atmosphere into space, atom by atom. Mars was not killed by a single disaster. It was dismantled, slowly, silently, inevitably. And as its atmosphere faded, the Sun's role in Mars' fate became impossible to ignore. Because the same star that gives life to planets can also take it away. To understand how Mars truly lost everything, we must look closer at the Sun itself and how its constant wind turned a living world into a barren one. Deep beneath the surface of every living planet is a heart. Not a heart of flesh, but of fire and metal. Molten iron churns thousands of kilometers below our feet, generating a powerful magnetic field that stretches far into space. It is invisible, but without it, life on Earth would not exist. Mars once had the same kind of heart. Liquid metal flowed, creating a global magnetic field strong enough to shield the planet from the Sun's most violent outbursts. For a time, Mars stood protected. But planets are not static, they age, and Mars aged faster than Earth. Because Mars was smaller, it lost heat more quickly. As energy leaked into space, the motion inside its core slowed. The molten iron that once powered its magnetic field began to cool, stiffen, and eventually stagnate. The Martian dynamo, the engine of its magnetic shield, was failing. At first, the magnetic field weakened. It no longer wrapped the planet evenly. Pockets of protection disappeared. Then, slowly, the global field collapsed entirely. Mars was left naked. This was not an event that left a visible scar. No crater, no explosion. Yet it was the single most devastating moment in the planet's history. Because the instant Mars lost its magnetosphere, the rules of survival changed. The Sun does not simply shine. It constantly releases a stream of charged particles, a solar wind moving at millions of kilometers per hour. On Earth, this wind is deflected, bent, and redirected by our magnetic field. It dances harmlessly along invisible lines, creating auroras near the poles. On Mars, there was nothing left to stop it. The solar wind slammed directly into the atmosphere. Each collision knocked particles loose. Each interaction stripped molecules away. Carbon dioxide, Mars' primary greenhouse gas, was torn apart and carried into space. Water vapor was split, its hydrogen escaping forever. The atmosphere began to thin, not in thousands of years, but over millions, a blink in planetary time. As the air disappeared, pressure dropped. Liquid water became unstable. Lakes evaporated, rivers slowed, then froze. Mars was losing the ability to be a world. With less atmosphere, surface temperatures fell further. Ice spread across the planet, dust storms grew more violent, unrestrained by moisture or vegetation. The planet entered a vicious cycle. Less atmosphere meant colder temperatures. Colder temperatures meant more frozen water. Frozen water meant less water vapor to trap heat. Less heat meant even thinner atmosphere. There was no mechanism left to reverse the trend. Earth avoided this fate because its magnetic field never failed, because its core stayed hot, because it kept recycling energy through plate tectonics and internal motion. Mars had no such safety net. Once its shield was gone, the Sun became unstoppable. The same star that had once warmed Mars' surface and fed its rivers was now slowly dismantling the planet particle by particle, breath by breath. Mars was not destroyed in fire, it was eroded by exposure, and the process continues even today. Spacecraft orbiting Mars have observed atmospheric particles still being stripped away by solar wind. The planet is still losing what little it has left. Mars is not just a dead world, it is a world still dying. The loss of the magnetic field was the moment Mars crossed from habitability into inevitability, from potential into decline, from a planet that could support life into a cautionary tale written in stone and dust. And once the shield was gone, one final collapse became unavoidable. Because without atmosphere, without warmth, and without protection, Mars could no longer hold on to the very thing that once made it alive: its water. Once Mars lost its magnetic shield, the sun was no longer just a distant star in the sky. It became an active force shaping the planet's fate. The solar wind, an endless stream of charged particles, never sleeps. It moves faster than sound, faster than storms, faster than any weather a planet can generate, and without a magnetic field to deflect it, Mars stood directly in its path. Every second, particles from the sun slammed into the upper layers of Mars' atmosphere. Not with violence you could see, but with persistence that could not be stopped. Each impact transferred energy, each collision knocked atoms loose. Over time, those atoms escaped Mars' gravity entirely, drifting off into space, never to return. This process had a name: atmospheric sputtering. But the name doesn't capture the reality. Mars was being sandblasted by a star. Carbon dioxide, the gas that once kept Mars warm, was stripped away, molecule by molecule. As it vanished, the planet's ability to trap heat collapsed, temperatures dropped. The planet cooled faster than it ever had before, and as the air thinned, something even more fragile was exposed: water. Liquid water cannot exist without pressure. It needs an atmosphere pressing down on it, holding it stable. As Mars' air leaked into space, surface pressure fell below the threshold where liquid water could survive. Rivers stopped flowing not because they ran dry, but because physics no longer allowed them to exist. Water on the surface began to boil at low temperatures, instantly turning into vapor. That vapor rose into the upper atmosphere where the solar wind was waiting. Ultraviolet radiation from the sun split water molecules apart. Hydrogen light and fast escaped into space. Oxygen, heavier and slower, reacted with rocks or was stripped away over time. Mars was losing its water permanently. What remained froze. Ice locked itself into the soil. Glaciers formed beneath the surface. Polar caps grew and retreated with the planet's slow, chaotic climate shifts. But frozen water is not dead water, it is imprisoned water, and Mars had no way to free it again. Earth avoids this fate because its magnetic field stands between the sun and its atmosphere, because its gravity is strong enough to hold on to gases, because its climate system constantly recycles heat, water, and air. Mars had none of these advantages left. The sun did not suddenly turn hostile. It simply continued doing what it has always done. The difference was that Mars could no longer defend itself. Over hundreds of millions of years, Mars transitioned from a warm, wet planet into a cold, dry desert. Not because the sun changed, but because Mars did. By the time the planet reached a new equilibrium, most of its atmosphere was gone, most of its water was gone, and with them, any realistic chance for surface life. All walls had crossed the point of no return. No volcanic eruption could rebuild the atmosphere fast enough. No warming event could thicken the air again. The feedback loops all pointed in one direction: colder, drier, deadlier. And yet, the planet did not become silent. Without water to stabilize the soil, dust storms began to dominate. They grew to global scales, covering the entire planet, blocking sunlight for weeks at a time. Mars became a world ruled by extremes: freezing nights, radiation-filled days, winds that carried dust across continents. The sun still rose and set. But now, it illuminated a planet that could no longer respond. This was the final betrayal of proximity. Mars was close enough to the sun to be stripped, but not close enough to stay warm, too far for stability, too near for safety. Mars had fallen into a cosmic middle ground, a danger zone where planets can lose everything. And the tragedy is this: Mars did nothing wrong. It followed the same rules as Earth. It formed from the same materials. It developed water, atmosphere, and energy. Slightly weaker, and slightly less protected. In the universe, slightly can be fatal. Yet beneath the surface, Mars still held secrets, because even on a dying world, not everything disappears at once. Some things endure. And if life ever existed on Mars, it would not have vanished with the rivers. It would have retreated, downward, into the ground, into the last places where water, warmth, and protection might still exist. To understand whether Mars was ever alive or could still be, we must now look at the planet as it is today. A frozen desert that still whispers of what it once was. As the sun continued stripping Mars' atmosphere away, the planet reached a moment that could not be reversed. Water was no longer cycling, it was no longer flowing, it was no longer part of a living system. Mars was losing its water forever. With atmospheric pressure collapsing, liquid water on the surface became impossible. Any remaining streams instantly vaporized. Lakes vanished not by drying up, but by breaking the laws of stability itself. Water either froze solid or escaped into space. Ultraviolet radiation from the sun penetrated deeper into Mars' thinning atmosphere. There was no longer enough air to block it, no magnetic shield to deflect it. When UV light struck water vapor, it tore the molecules apart. Hydrogen, light and fast, rose upward and escaped Mars' weak gravity. Oxygen, heavier and reactive, bonded with iron-rich rocks, slowly rusting the planet red. This is why Mars is red. Not because of fire, not because of lava, but because of oxidation, the slow chemical record of water being lost. Mars didn't just lose water from the surface. It lost it from the sky, from the air, from the planet itself. Some water retreated underground, freezing into vast subsurface reservoirs. Ice became trapped beneath layers of soil, protected from radiation but locked away from the climate. Polar caps grew, shrank, and grew again as Mars' axis tilted chaotically over millions of years. Unlike Earth, Mars lacks a large moon to stabilize its tilt. So its climate swung wildly, sometimes pushing ice toward the equator, sometimes pulling it back to the poles. But these were temporary redistributions. The total amount of water was always decreasing. Mars had entered a one-way process. A planet without a strong atmosphere cannot hold liquid water. A planet without liquid water cannot regulate temperature. And a planet without temperature regulation cannot sustain life on the surface. Mars crossed all three thresholds. The feedback loops were now complete. Less atmosphere led to lower pressure. Lower pressure led to water loss. Water loss led to colder temperatures. Colder temperatures led to even thinner atmosphere. Nothing could stop it. Volcanoes had gone quiet. There was no longer a way to rebuild what had been lost. Mars' internal engine, the one that once kept it alive, had shut down. The planet became geologically dormant. No plate tectonics to recycle carbon. No widespread volcanism to replenish gases. No oceans to store heat. Mars became static, frozen, exposed. Radiation levels soared. Temperatures dropped far below freezing. Liquid water became a rare temporary event if it appeared at all. Any surviving organisms would have been forced underground, where ice, rock, and soil could offer protection, and then even those refuges began to fail. As the planet cooled further, heat from the interior faded. Subsurface environments grew colder and drier. Chemical energy sources dwindled. Mars was not just losing water, it was losing time. What remained was a fossil planet, a world frozen in the moment it failed. Its riverbeds hardened into stone. Its lake floors preserved sediments like pages in a history book. Its deltas remained exactly where water once slowed and spread. Mars became a museum of habitability, a place where the evidence of a living world still exists, even though the world itself no longer does. Today, when we look at Mars, we are not just seeing a dead planet. We are seeing the end result of a slow planetary collapse, one that took hundreds of millions of years to complete. And yet, Mars still holds answers, because in its rocks, its ice, and its ancient terrain lies the record of everything that went wrong. Mars is not important because it failed. Mars is important because it shows us how close success can come and how fragile it truly is. To fully understand the consequences of that failure, we must now look at Mars as it exists today. A frozen desert world still shaped by the ghosts of rivers, oceans, and a climate that once worked. What remains today is not the Mars that once was, but the shadow of it. A planet locked in cold silence. Modern Mars is a world of extremes. Average temperatures hover far below freezing. At night, the cold is so intense that carbon dioxide itself freezes and falls from the sky like snow. The atmosphere, once thick enough to hold warmth and water, is now barely there. It offers almost no insulation, no protection, no stability. Daytime heat escapes instantly into space, and the planet swings violently between warmth and cold. Radiation rains down on the surface, unfiltered. Cosmic rays and solar particles strike the ground directly, breaking chemical bonds and sterilizing the soil. For life as we know it, the surface of Mars is hostile beyond survival. And yet, Mars is not quiet. Without oceans or forests to slow the wind, dust dominates the planet. Fine particles, smaller than grains of sand, are lifted easily into the air, carried across continents. Local dust storms grow into regional ones. Regional storms merge into global events, sometimes enveloping the entire planet for weeks. These storms do not just obscure the surface, they reshape it. Over millions of years, wind has sculpted Mars into sharp ridges, towering dunes, and vast plains of drifting dust. The planet is constantly being erased and rewritten, though never healed. The rivers are gone, but their paths remain. From orbit, we see them clearly, ancient channels cutting through rock. All delta fans frozen in time. Lake beds preserved like imprints of vanished worlds. These features are not artistic illusions. They are geological records, undeniable proof that Mars once functioned as a system, not a wasteland. In some places, the surface looks young and fresh. In others, it is ancient beyond comprehension. Mars lacks plate tectonics, so its crust does not recycle like Earth's. Once a feature forms, it stays. This is why Mars is so valuable to science. It remembers everything. Earth erases its past through erosion, subduction, and tectonic motion. Mars preserves its history openly, exposed beneath thin air and drifting dust. Beneath the surface, Mars is not entirely dry. Radar scans have revealed vast deposits of ice buried under soil and rock. In some regions, frozen water lies just meters below the ground. This ice is not evidence of a living planet, but it is evidence of a planet that once lived. Occasionally, seasonal changes cause small amounts of briny liquid water to form briefly on slopes, but these flows are temporary, unstable, and likely toxic to life. Mars today cannot sustain a global water cycle. It cannot maintain surface oceans. It cannot protect biology from radiation. It is a planet frozen in a failed state. And yet, Mars still tempts us with possibility. Because beneath its surface, shielded from radiation, conditions may be different. Underground, temperatures are more stable. Ice can melt under pressure. Chemical reactions can occur slowly over time. If life ever existed on Mars, this is where it would have gone, downward, into hiding. Mars is no longer a planet of growth. It is a planet of preservation. Every crater, every ridge, every mineral layer is a chapter in a story that Earth can no longer tell about itself. Mars shows us what a planet looks like after hope fades, but before memory disappears. And that raises the question scientists cannot ignore. If Mars once had everything needed for life, if it held water, warmth, and chemistry for millions of years, then did life ever actually begin there? Or did Mars fail just moments before crossing that final threshold? To answer that, we must now follow the evidence not across landscapes, but into chemistry itself. Because the greatest mystery of Mars is not what it lost, but whether it ever truly lived at all. This is the question that turns Mars from a dead planet into a mystery. Not how Mars died, but whether it ever lived. Because if life could begin on Mars, then life may not be rare in the universe. And if life failed there, then survival may be far more fragile than we imagine. For decades, scientists avoided this question. It was too big, too uncertain. But Mars would not let it go. Hidden within its rocks are chemical signatures that do not belong to a lifeless world. Organic molecules, carbon-based compounds essential to life have been detected in ancient Martian sediments. These molecules do not prove life existed, but they prove something just as important. Mars had the chemistry required for life to begin. On Earth, life emerged astonishingly fast. Almost as soon as liquid water stabilized, biology appeared. This suggests that life does not need perfection, only opportunity. And Mars had that opportunity. Early Mars had lakes that lasted thousands of years, river systems that flowed repeatedly, clay-rich environments that protected delicate molecules from radiation. These are not random conditions. They are the exact environments where life thrives on Earth today. If microbial life ever appeared on Mars, it would have been simple, single-celled, resilient. Life does not begin as forests or animals. It begins quietly feeding on chemical gradients, adapting slowly, multiplying invisibly, and Mars had time. But evidence of life does not announce itself clearly after billions of years of radiation and erosion. It hides. Fossil microbes do not leave bones, they leave chemistry, isotopic ratios, mineral patterns, textures in rock that resemble ancient microbial mats. These are subtle clues, and they are easy to erase. When Mars lost its atmosphere, radiation began sterilizing the surface. Any biological signatures left exposed would have been destroyed. That is why scientists look downward. Ancient sediments remain protected. There, chemical fingerprints may still survive. Mars may no longer be alive, but it may still remember life. And then there is the most unsettling possibility of all. What if life didn't just exist on Mars? What if it still exists? Deep underground, liquid water could persist under pressure. Chemical energy sources could still power slow metabolism. Life on Earth thrives in far harsher conditions: deep oceans, radioactive waste, frozen tundra. If Mars ever hosted life, extinction would not have been instant. Life would have retreated, adapted, waited, but waiting has limits. As Mars continued cooling, even subsurface environments became less stable. Water froze, energy sources vanished. If life survived, it would be rare, localized, possibly extinct today. It is a parallel experiment. Two worlds formed side by side. One became alive. The other may have tried and failed. Understanding that difference matters. Because Mars teaches us that habitability is not permanent, it can be lost, and that realization forces us to turn the question inward. Why did Earth succeed where Mars failed? What protected Earth from the same fate? And most importantly, is Earth's advantage permanent or temporary? Mars is not just a story about another planet. It is a warning encoded in stone. To truly understand that warning, we must now compare the two worlds directly, not emotionally, not philosophically, but mechanically, because the difference between life and lifelessness may come down to just a few planetary traits. Traits Earth has, traits Mars lost. When we compare Earth and Mars today, the difference feels absolute. One is alive, the other is silent, but the truth is more unsettling. Earth did not win because it was perfect. Earth survived because it was just slightly better equipped to endure time. The first difference is size. Earth is larger than Mars, about twice the diameter, and more than 10 times the mass. That extra mass changed everything. A larger planet holds heat longer. Its core cools more slowly. And that slow cooling kept Earth's interior active for billions of years. This internal heat drives Earth's magnetic field, the invisible shield that Mars lost. While Mars' core froze and its magnetic field collapsed, Earth's core kept moving. Liquid iron continued flowing, generating a powerful magnetosphere that deflects solar wind even today. This single difference protected Earth's atmosphere from being stripped away. An atmosphere is survival. Earth's gravity also played a role. Stronger gravity meant gases were less likely to escape into space. Water vapor stayed. Carbon dioxide stayed. Earth could breathe without losing its breath. But protection alone is not enough. The second critical advantage Earth had was motion. Earth has plate tectonics. Its surface is broken into massive plates that move, collide, separate, and recycle material between the surface and the interior. Mars does not. On Earth, carbon dioxide is constantly pulled out of the atmosphere by weathering and stored in rocks. Then, through volcanism, it is released back into the air. This carbon cycle stabilizes climate over millions of years. When Earth cools, carbon dioxide builds up, warming the planet. When it warms, carbon dioxide is removed, cooling it down. Mars had no such system. Once its volcanism slowed and stopped, there was no way to regulate climate. No recycling, no second chance. Earth's oceans provided another layer of protection. Water stores heat. It moderates temperature. It stabilizes weather. Mars lost its oceans early. Without them, temperature swings became extreme. The planet grew colder faster. Ice locked away what little heat remained, and then there is the moon. Earth's large moon stabilizes our planet's tilt, preventing extreme climate swings. Mars has no such stabilizer. Over millions of years, Mars' axis tilted wildly, causing dramatic shifts in climate. Ice migrated unpredictably. Atmospheric pressure fluctuated. Stability vanished. Earth had stability, not perfection. Stability. Life does not require ideal conditions. It requires consistency. Mars lost that consistency. Earth also benefited from timing. The sun was more violent in its early years, emitting stronger solar winds. Mars lost its magnetic field during this dangerous phase. By the time the sun stabilized, Earth's defenses were already in place. Mars was exposed at the worst possible moment. None of these advantages alone guaranteed Earth's survival. Together, they made the difference. Earth stayed warm enough, protected enough. Mars fell just short in every category. And here is the most important truth: Earth is not immune. Earth's magnetic field has flipped many times. Its climate has nearly collapsed more than once. Mass extinctions have wiped out most life repeatedly. Earth is alive because it keeps balancing on a narrow edge between heat and cold, loss and renewal, chaos and order. Mars shows us what happens when a planet slips off that edge, which brings us to the final and most uncomfortable question. If Mars was once like Earth, and Earth survived only by a small margin, then what does Mars tell us about our future? Because planets do not need explosions to die. They only need imbalance. Mars is important because it almost wasn't. For a brief moment in cosmic time, Mars stood on the edge of becoming a living world. It had water, it had warmth, it had chemistry, it even had time, and still it failed. That failure forces us to confront a difficult truth about Earth. Life is not guaranteed. We often imagine planetary death as something dramatic, a massive asteroid, a supernova, a sudden catastrophe. But Mars teaches us something far more unsettling. Planets don't usually die loudly. They fade. They lose protection first, then balance, then memory. Mars did not explode. It did not burn. It slowly forgot how to be a world, and the process began with something invisible: a weakening core, a fading magnetic field, an atmosphere thinning molecule by molecule. By the time the surface changed, the outcome was already decided. Mars shows us that habitability is not a permanent state. It is a condition that must be maintained. Earth today feels stable, but it survives by constantly correcting itself. Its climate cycles, its magnetic field shields it. Its oceans regulate heat. Its geology recycles gases. None of these systems are infinite. Earth's magnetic field has weakened before. Its climate has swung violently. Its atmosphere has changed composition many times. The difference between Earth and Mars is not destiny, it is margin. Earth has more margin, for now. Mars reminds us that losing an atmosphere is not just a planetary problem, it is a biological extinction event on a global scale. Without air, water cannot flow. Without water, chemistry stops. Without chemistry, life ends. Mars crossed that threshold slowly, so slowly that, if we were watching in real time, we might not have noticed. That is the real warning. Change does not need to be fast to be fatal. A future where oceans retreat, where protection weakens, where balance collapses. Mars is proof that planets can look healthy right before they fail. And yet, Mars is not just a warning, it is also a gift, because Mars preserved what Earth erased. Its rocks remember the early solar system. Its surface remembers water. Its minerals remember chemistry. By studying Mars, we learn how rare survival truly is. We learn that life is not inevitable, but neither is extinction. Earth survived because it stayed active, because it stayed protected, because it stayed balanced long enough for life to adapt and endure. Mars tells us what happens when those conditions slip. Not with drama, but with silence. Today, Mars orbits the sun as it always has. The same sun that once warmed its rivers now shines on dust and ice. The planet is still there, but the world is gone. And as we look up at the night sky from Earth at that small red point of light, we are not just seeing a distant planet. We are seeing a message from the past, a reminder that being alive is not a permanent state. It is something a planet must earn, every day for billions of years. Mars almost made it. Earth still is. The question that remains is not whether Mars was once like Earth. The question is whether Earth will always remain unlike Mars.